So I'd like to begin this video off with a question. If the moon orbits around the Earth because of Earth's gravitational pull, then why the hell do the astronauts on the International Space Station float? That just does not make sense at all. But don't worry, I have the answer. And the answer is that the astronauts, as well as the International Space Stations, are falling, not floating. And because they're all falling at the same rate, it appears that the astronauts are floating. Now, this International Space Station and the astronauts, although they're free falling towards the Earth, it never crashes onto the Earth. And this is because it has a fast horizontal velocity of 27,580 kilometers per hour. And it uses speed to fight against gravity. So it never crashes onto Earth, and it instead stays in orbit around the Earth. So how exactly does this all relate to artificial gravity? Unfortunately for us, due to billions and billions of years of evolution, our body works best when the gravitational force, or G-force, is close to 1g. Now, the ISS, as well as the astronauts on it, experience a G-force of 0.89g, which is close to 1g. But again, because everything's falling and accelerating at the same rate, this means that the G-force is closer to 0. And because the G-force is close to 0, the astronauts experience weightlessness, which can cause some complications. This includes muscle atrophy, deterioration of skeleton, as well as osteoporosis. So how exactly can we send astronauts into space for months, years, even decades without severe medical interventions or modifying their genes? Well, the answer is creating artificial gravity. So how exactly does artificial gravity work? Back to the Einsteinian era, Albert Einstein proposed the notion of the equivalence principle of general relativity, where he states that the gravitational force on Earth will feel no different or is indistinguishable from a pseudo-force caused by an accelerated frame of reference, meaning that if gravitational mass equals to inertial mass, that means that the observer will feel no different from gravity on Earth than the pseudo-force caused by an accelerated frame of reference. Now, in order to create the pseudo-force or artificial gravity, we need an accelerated frame of reference. And there are three major types of acceleration. The first is gravitational. So gravitational is just basically gravity we experience on Earth. Second is linear. And with linear, what we can do is launch a spacecraft that accelerates at 1g. But it's not the most ideal because, first of all, you run out of fuel. Second of all, we haven't been able to launch anything with the acceleration of 1g, and it's pretty hard to do. Third, if you were to accelerate at 1g, that means that at some point you'll reach somewhere close to the speed of light. And when that happens, time acts weirdly. Third is rotation. Now, rotation is more practical than linear acceleration. Let me provide you with some examples. The Gravitron, as well as Nightmares at Canada's Wonderland. From an inertial frame of reference, both of these rides, the walls appear to push hard on your back. And this is because your body is going to fly off in a tangent due to inertia. But the wall prevents you from doing that because it turns you into a circle and applies force onto you. And it applies a centripetal force onto your back, which prevents you from flying off of the ride. From a rotating frame of reference, it doesn't seem like anything is spinning. And in fact, it feels like there's a mysterious force pushing you against the wall. And this is called a centrifugal force, and it is a fictitious one. Now, what if we took this notion and applied it to a spacecraft? So instead of our backs being pushed against the wall, what if we changed that wall into a floor and now we're standing on the floor? Boom! Artificial gravity. But because this is rotational and not linear or gravitational acceleration, we might experience some disorienting effects that we don't typically experience on Earth. Unless you plan on not moving at all in the spacecraft, because the Coriolis effect only affects things that are in motion. The Coriolis effect is an apparent force that acts on objects that move in a rotating frame of reference, and it acts perpendicular to the velocity of an object. This actually affects the fluids in your ear, and because of that, you might experience dizziness, nausea, and maybe vomiting. Another thing that the Coriolis effect does is that whenever something is falling towards the ground, it tends to curve. So how exactly can we minimize the Coriolis effect? Well, in order to minimize that, we would have to increase the radius. And when we increase the radius, we have to make sure that the rate of rotation is correct so that we can have 1g acceleration. And that will actually require a massive ship, which is a lot of money and takes up a lot of resources. So hopefully in the future, we can build a spacecraft that has artificial gravity, but as of now, it's technically feasible, but not economically feasible.